Welcome to our talk on the evaluation of redirect tracking and link usage. My name is Martin Koop, earlier known as Dobczynski, and together with my colleague Eric Taves, we will present you our research results. First, some basics about redirects. The intended usage is to redirect the user to another valid or updated URL. Here, the server usually sends an HTTP status code for a temporary or permanent moved URL. In our evaluation of the Alexa 50K, we saw, for example, different behavior on the initial loading of websites. Here, 77% upgraded from an HTTP to a secured connection. 25% redirected within the same domain, for example, adding or removing a subdomain. As you can see in our example, here the server removed the subdomain. Following, 5% redirected to a different domain, and in 1% of the cases, the server redirected to a country-specific domain. There are also client-side redirects like HTML meta refresh using JavaScript or PHP scripts. All of them are all covered in our evaluation, but are a bit more difficult to recognize since there are no HTTP status codes our script can listen to. In this case, we need to monitor the URL bar for changes. But redirects are also misused to harm the user and were already studied in different research. For example, on phishing attacks, where an attacker is redirecting to a malicious domain, to deliver malware through drive-by download attacks, or to deliver malicious advertising and spam. This is done to route the user through different servers not yet being blocked by security add-ons and to hide malicious websites and their content. In addition, there exists a form of tracking hidden behind ordinary website links, not clearly visible to the user. Here, the tracker redirects the user through a chain of potential tracking servers to collect valuable metadata like website content, topic, or user interest, and also to set first-party cookies, which are more difficult to block. Here we will visualize the method. First, the user clicks on the link entitled with Job Search, which will open the DoubleClick website. Here, a cookie is being saved and the website automatically redirects the user to another subdomain of DoubleClick, again storing a cookie with an additional ID and redirecting the user again to a third-party domain, addition.com. Here, the cookie ID with the previously set ID is being stored, and at some point, finally, an automatic redirect will lead the user to the intended website which he thought being leading to. With our real-life example, we will show you this procedure. So within this website, the user is clicking on one of the links. He wanted to get some more content, and within a millisecond, the intended website is being loaded. What the user did not see is that in between, many different redirects happened and some cookies have been saved on his machine. So the problem is that within those different redirects, many different websites can save the user cookies and metadata. The experimental setup we used for our study will now be explained by my colleague Eric Taves.
To conduct our experiments, we created a custom crawler based on OpenWPM. OpenWPM is a framework based on Firefox and Selenium. It's written in Python, TypeScript, and JavaScript. Basically, OpenWPM allows you to take Firefox, send it to a website, and then interact with that website. For example, you can scroll up and down, you can move the mouse around, and you can click on elements. And while you do that, all the important events in Firefox are recorded. We extended OpenWPM and added a few new features. For example, now it's able to collect the links It's able to monitor more details of HTTP requests and also give us more information about cookies that are set. We use Firefox within OpenWPM with two different cookie settings. We use the always setting, which is the default setting of Firefox, and we use the never setting. In the never setting, only first-party cookies are accepted. Third-party cookies are never accepted. And we created a distributed architecture based on Celery, RabbitMQ, and Docker. With the distributed architecture, we are able to run many OpenWPM instances on many machines in parallel, which allows us to crawl the web much faster than on a single machine. To examine individual website, we do the following. We open the website in Firefox and then we wait until the page is fully loaded. Once this is done, we perform some kind of bot mitigation. That means we move the mouse around, we scroll down, and then we wait for 10 seconds. We do that because some websites tend to load additional data after the main page is loaded, and that might be triggered by scrolling down or by moving the mouse around. Once this is done, then we try to collect all links from the DOM. That means we basically get all A tags from the DOM, including those that are surrounding image tags. So links can also be images, but doesn't have to be text, but it can be text. Other tags, such as, for example, div tags with an onClick JavaScript event, which may then trigger the loading of another website, are not considered to be links. So for us, links are only A tags. Once we have all the links, we try to find the links that we would like to click on. For that, we try to select only visible links. So for example, there might be some links in the DOM, but those links are invisible because they have been set to an invisible mode by using the corresponding CSS attributes. We try to prioritize the links that have already been visited on that website with a different setting. So for example, when we're already on the website and we already visited the link to a.com with the never setting, we now try to prioritize this link with the always setting. And we try to prioritize links that point to domains and hosts that were not yet visited, which means we try to maximize the number of different domains and hosts in our crawl. And which results we achieved with that is something Martin will now explain.
The month-long crawl of the Alexa 50K website list resulted in nearly 1,260,000 individual website crawls, in which our crawler clicked on nearly 1 million links, 56% of them embedded on image tags. Looking at the graphic, most of the website had 4 to 31 external links we could click on, and 10% of the website had no links. On average, our crawler clicked on 10 external links on each page it visited. As pre-studies showed, 95% of tracking redirects occurred on external links. So in order to save crawling time and get better results, we focused only on clicking external links. In our crawling data, we recorded over 100,000 redirect chains with at least one external domain. Here, the cookie configuration, always or never, showed no significant difference in the amount of links being opened. In the beginning, we thought that trackers might add more external tracking links depending on the cookie setting. This was not the case. To classify tracking cookies, we used the EasyList and EasyPrivacyList, as well as a modified classification suggested by Engelhardt et al., where a cookie is a tracker if it's not a session cookie and the lifetime is longer than 90 days, the cookie value is larger than 8 bytes, and the different cookie values we observed during the crawl differ by at most 25%, and we have only seen the cookie in a single visit. Also, the similarity of the values compared to other values of the same cookie, according to the Radcliffe-Oberthaupt string comparison algorithm, is 66 or less for at least half of the other values we observed in our other visits. Using our metrics, we built a table with the top 30 redirect trackers and the total number of redirects observed during the crawl, and the number of websites the tracker was embedded and involved in the redirect chain. We then compared the two cookie settings, always block third-party cookies and never block third-party cookies, as well as compared the cookies being set in the initial page load as well as during the redirect. What we notice is that there are a lot of redirects on many websites we visited, and also we noticed that there are no cookies being set in the initial page load where third-party cookies are blocked. A key finding is that most cookies are being set during the redirect in the never cookie configuration where third-party cookies are being blocked. This indicates that redirect trackers exploit this setting and definitely will store a first-party cookie on the user's machine. We then applied our tracking classifier, showing that the result nearly is the same as the EasyList filter blocking third-party tracking elements. In addition, we see that there are also some trackers that do not save any cookies on the user's machine, like YouTube or Google, which are usually a shortener for their own service. We also looked into the Ghostery plugin and Safari Intelligent Tracking Prevention, claiming to block redirect tracking as well. In our studies, only 30% of the cookies could be blocked using both countermeasures. The second focus of our research was to evaluate the redirect tracker network. For this, we plotted a graph of the top 100 redirectors. Here, an edge is drawn when a redirect from A to B happened. We also weighted and color-coded the edges by the number of redirects occurred. In this example, buy-sell ads redirects to DoubleClick with 500 redirect connections. The node size depicts the out degree of connections, where in this graph, DoubleClick has 22 connections to other redirect domains. We then used the Lavane community detection method to visualize clusters of redirect trackers. The algorithm found 10 main communities, between 3 and 21 nodes. One of the biggest clusters forms around Bitly. It has connections to Amazon Ad System, YouTube, Smart Ad Serve, or Google.
So let's talk about countermeasures. There are a few ways how we can counter this type of tracking. For example, we can try to rewrite target URLs and links. So when you have a website loaded in your browser, then in your DOM, there are certain links, that means A tags, that point to known redirect trackers. And for some of those redirect trackers, it's actually possible to guess the final destination of the link without having to contact the redirect tracker. You can just see it from the URL. And then we can have, for example, a script that rewrites all known redirect tracker links, or some of them, with their final destinations. So when somebody clicks on the link, the browser goes right to the final destination and the redirect tracker is never contacted. Alternatively, we do not have to do it in the DOM, but we could also try to dynamically rewrite HTTP requests in the browser. Another countermeasure would be to kind of still contact the tracker, but to block cookies from known redirect trackers by, for example, having a filter list like for an ad blocker. We could have a list of the most common 100 or 1000 redirect trackers, and then we could simply block all cookies from those domains. Another alternative would be to disable pop-ups and block ads. So a lot of those redirect tracking links, they are somewhere within an advertisement, and when we block advertisements in general, then there will be fewer links on the website that point to redirect trackers. And actually, that also improves the user experience because ads are in general mostly annoying. We could also have some kind of, first-party isolation per website for cookies, but that doesn't really work when the redirect trackers are doing something like cookie syncing or something like that. So that's not a very good countermeasure. And the most creative way is probably what Apple is doing with Safari, and I think they are monitoring interaction with websites. So when you go to a redirect tracker, but that tracker simply forwards you, but you never interacted with an element coming from that redirect tracker by, for example, clicking on something or, scrolling up or down or something like that, then cookies from those domains are deleted after a while. To conclude, we figured out that 11.6% of the Alexa top 50,000 domains contain links to the top 100 redirect trackers. Those trackers are able to send cookies in your browser even when you configured your browser to accept first-party cookies only and you have ad blocking enabled. That gives them a huge potential for tracking compared to, typical third-party trackers. And those trackers, they form some kind of community network, which means they could potentially share their data, which makes them even more dangerous. We are sure that you have a lot of questions about our research and about our paper. That's why I and Martin are now online in the Q&A session, so you can now start asking your questions and we will try to answer them as good as possible.